Okay, hopefully your conversions weren't too bad. We are on our next page. Sorry, it's 27. Okay, so we're going to take some notes on some gas laws. I apologize that you have to listen to me do this, but at least you're getting the information and we're not falling too behind. All right, so gas laws. So we're going to divide our paper up into 4 squares. Okay, it's down the middle. So you should have a total of 4 squares. All right, we're going to go through 3 main gas laws that you need to be familiar with. We'll go through the other one on Friday. Okay, that gas law, we are going to be looking at pressure and volume. And again, this was the one you had for homework. Okay, pressure and volume. And what we are keeping the same, and it is not changing, right? We may make the space bigger, so our pressure is going to go down because there's going to be less collisions. And then what's staying constant, so what will be constant and not changing, is going to be the temperature and the number of particles. Those aren't changing. So our equation for this is P1 V1 equals P2 V2. Okay, and this is known as Boyle's law. You won't have to necessarily know the name, and you won't have to memorize the equation. They'll be given to you on a sheet. You need to know when to use that equation. Okay. So in your assignment last night, when you talked about pressure and volume, as that space gets bigger, right, there's more room for our particles to move around. So that relationship is an inverse relationship. Or this is an inverse relationship. Right, as our volume increases, that space gets bigger, our pressure is going to decrease. Okay, and also to think about this as an inverse relationship, okay, using this gas law, is if, I'll plug in some fake numbers for instance, if the volume, so say our pressure was like 1 atm, so I'm plugging in some fake numbers, and our volume was 5 liters. And we want to figure out that pressure if the volume doubled. So if they're nice things where you can see the relationship, so we can see here our 5 liters doubled, right, times 2. Well, since it's an inverse relationship, your pressure, your pressure is going to decrease by a factor of 1/2. Okay, so it's inversely related, right? Because the inverse of 2 is 1/2. Okay, so you can look at that too instead of having to do any math if you can see the relationship. Okay, if not, right, we can plug it into a problem. So our example problem that I'm going to give you, you can write it down so we can see how we should approach our problems. So we have a gas, and it occupies 3.86 liters at 0.750 atm. What pressure will the volume be 4.86 liters. All right, so when you do this, you can do it, just depends on how you like to do it. Due to space, when you are reading these problems, I want you to circle and identify what's being given to you, okay? So if we look at our problem, okay, a gas occupies 3.86 liters, right? Liters is our unit, so you should be able to look at that and say, that's a volume. Okay, at 0.750 atm. Well, atms is a unit of pressure, so this is a pressure. And then it's asking what pressure. So we also don't know the next pressure. What pressure will the volume be for 4.86 liters? Okay, now it doesn't matter what order like if you label them 1 or 2, as long as they're paired up correctly. So this gas occupies 3.86 liters at that pressure, so they need to go together. So I'm going to say that's V1 and that's P1, right? Which would make this one, we want to figure out the pressure P2 if the volume is changed to 4.86 liters. So then we can plug it in. And your units, you don't have to convert anything because they just need to match. So our liters are liters, and then our answer would be in ATMs since that one's in ATMs. So I'm going to plug in. I have 0.750 ATMs times 3.86 liters equals, I don't know my P2, and then my new volume is 4.86 liters. Right, so this is our X, this is our unknown, what we're trying to solve for. How would I get that by itself? I would divide both sides by 4.86 liters. 4.86 liters, so then that goes away. Right, we can put that in our calculator. 7.50 times 3.86 equals, divided by 3.86 or 4.86, sorry. So P2 is going to equal 3.633, so our answer should have 3.596 ATMs. Sorry, I ran out of room right there. Okay. That's how we can use Boyle's law, right? If we are reading a problem and they are only giving us pressure and volume. All right, and the last thing about this type of relationship is that since it is an inverse, right, if we change the volume, if the volume increases, our pressure is going to decrease. So it is an inverse relationship. So there's that graph. Sorry, forgot about that. All right, our second one. And again, if you miss something, we can come up and grab it. We're going to look at temp. We have 3 of these to do. Temp and volume. Okay, and so if we're comparing temperature and volume, we can assume that our pressure and number of particles is constant. So they're not changing. Okay. So our equation for this looks a little different. It is V1 over T1 equals V2 over T2. That's your equation there. Okay, and this is Charles's law. Okay, super important about this, your temperature before you plug it in must be in Kelvin. If it is not, your answer will end up wrong. So your temp must be in Kelvin. And we just practiced that, right? How to get temperature into Kelvin. Kelvin equals degrees Celsius plus 273. All right, and this is a direct relationship, right? If our temperature goes up, those particles are going to move faster. We're keeping pressure constant, so that space is going to get bigger, right? They're going to need more space. So this is a direct relationship. So if the if the temperature increases, our volume is going to increase, right? Because if you increase the volume, it's not necessarily going to change the temperature of something. So, right, that volume is dependent on that temperature. Okay, and since this is a direct relationship, right, doesn't need to be very big. We know our temperature is the independent and our volume, and it is a direct relationship. Okay. And since it's direct, I'll kind of give you another example like we did for boils. Is if you're looking at this and you have, I don't know, say we'll use 5 liters over 100 Kelvin, we've already converted, and we want to figure out what our new volume is going to be, and say our temperature is 200, right? We can look at that, and we know this is doubling, and since it's a direct relationship, this is going to double as well. So really, looking at something easy like that, you don't have to do any math. Your V2, right, doubling 5 would give us 10 liters. It's a direct relationship. So whatever happens there, right, would happen there. Or, right, if it's not that easy and you set up your problem and you're like, oh, I don't see any relationship, right, we can just plug in our numbers. So here's our example. What will the volume be of a gas sample at 100 degrees Celsius if its volume is 9 liters at 0 degrees Celsius? Okay, so a couple things. First thing, when you read a problem, you want to label, right? So we know what will the volume be. So we know we're definitely trying to find a volume of a gas sample at 100 degrees Celsius. Okay, and we know this has to be converted. So 100 plus 273, that is easy, 373. So that would be one of my temperatures. Okay, so what will the volume be of a gas sample at 100 degrees Celsius if its volume is 9 liters, another volume, at 0 degrees Celsius? And again, your temperature needs to be converted to Kelvin. 0 plus 273 is 273, so that one's easy. So they're asking, what will the volume of a gas be? So you can say, we don't know V2, and we know that this temperature is also T2. Okay, so the one that we found right here, 373, is T2. If its volume is at, so it's currently at 9 liters, so V1, and this would be our T1. Now, if you flopped those and you said, oh, I'm going to say this is V1 and T1 and this is V2 and T2, that's completely okay. What matters is that they're paired up together correctly, right? So it's important to read those words. So when we plug in, I can zoom in. We got 9 liters over 273 Kelvin equals, we don't know our second volume, over 373 Kelvin. Okay, now, right, depending on how comfortable you are with your math skills, there's a lot of different ways you can do this, but I'm going to keep it consistent, and I'm going to cross multiply. Okay, so I get V2, or X, times 273 equals 9 liters times 373 Kelvin. Makes it a little bit easier. How do we get V2 by itself? Divide by 273. Divide by 273. So we're going to go 9 times 373 divided by 273 gives us, and you should try this to make sure, okay, and 2 sig figs, so I get 12 liters. All right, if Mrs. Parker needs to pause, you guys need a stretch break, feel free, okay? But we're gonna do one last one, and then we are done. So in your bottom left-hand square, scooch down there. We're gonna look at temperature and pressure. And with that said, temperature and pressure, that means our other variables are constant. So what are we not changing? Would definitely be our number of particles and our volume. So the volume, right, you can think about we're in a non-flexible container. It's not going to get bigger. All right. So this relationship is P1 over T1 equals P2 over T2. Okay, and this is Gay-Lussac's law. Okay, and again, right, you got temp in here. Your temp needs to be in Kelvin. Okay. And this is also a direct relationship. So, right, the temperature is the independent. So if the temp goes up, right, our particles are going to be moving faster. So there are going to be more collisions and our pressure goes up, right? Because if we decrease the pressure, it doesn't change the temperature of the particles. So that pressure depends on temperature, okay? So for direct relationships, just like in Charles, right, we have our temp as our independent. That pressure depends on that, and it is a direct relationship. And again, right, we can look at this, right, and if you're given something easy like 6 ATMs over 300 Kelvin, and we want to know what P2 is, and you can do this also on the bottom, P2, and our temperature doubles, right, direct relationship, so then that means our pressure would have to double, so P2 would be 12 ATMs, right, direct relationship. All right, last part, and we are done. You guys are doing great, okay? Here's our example. We'll solve our problem, okay? We have a 20-liter container. Contains 3 ATMs. of gas at 27 degrees Celsius. What is the pressure at at 627 degrees Celsius. Okay, so they don't give you another volume, right? Volume's not changing, so when you read it, you're like, oh, that's a volume. Great, but they're not giving you a second one, so we can ignore it. We're assuming, right, it's held constant. So we have 3 ATMs at 27 degrees Celsius, and we want to know what that pressure is at 627. So if we add 627 plus 273, we get 900 Kelvin, right? Remember, we got to convert these to Kelvin. 27 degrees Celsius plus 273, so that temperature would be 300 Kelvin. And then we got our P1 up here. So we can plug in 3 ATMs over 300 Kelvin equals P2 over 900 Kelvin. Okay, again, you can cross multiply, or, sorry, can't see all that, or you can say, hey, this tripled, so then this should triple. So my P2 would be 9 ATMs. Okay. So those are our 3. I know that was a lot of information, so take a sec, and then you're going to practice doing these problems on a worksheet given to you. So you can give some practice on doing all this fun stuff. Thanks.